this video, we will be discussing about redundant connection. In this problem, a tree is an undirected graph that is connected and has no cycles. You are given a graph that started as a tree with n nodes labeled from 1 to n with one additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. Basically, there is no self loop of that edge. The graph is represented as an array edges of length n where edges of I equals to ai comma bi indicates that there is an edge between nodes ai and bi in the graph. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. So what they are saying is that in the input we are given this edges vector, right? Now these edges are the edges connecting these nodes. Now this particular thing was previously a tree and then they added one edge to it due to which it became a graph, right? Now we need to identify one such edge from this graph such that if we remove that particular edge, then this particular graph again becomes a tree, right? And if there are multiple such edges, then we need to return the last edge which appears in this input, right? So if we see over here, see what are the properties of a tree. The properties of a tree are that it does not have any cycle, right? And it is a single connected component. Whereas in a graph, we can have multiple components, and in a graph, we can also have a cycle, right? Since they are saying that this particular structure was previously a tree, then that means there were no cycle, and then they introduced one edge to it which didn't exist already before, right? So basically, what does a tree look like? A tree looks like this, right? Now it's not necessary that it is a binary tree, it can be this also, right? Now they are saying they introduced an edge which was not previously present. So whenever they will introduce an edge, it will always form a cycle. For example, if I put an edge here, then this is a cycle. If I put here, then this is a cycle, right? So basically, if in that particular tree one edge which didn't exist before was added into the tree, then it now created a cycle in our graph, right? That is why it became a graph now, right? So if you see over here, this is a cycle. There is an edge from 1 to 2, then 1 to 3, and then 2 to 3. This is an undirected graph, right? So we can say from 1 to 2 also and from 2 to 1 also, right? So this is a cycle over here. And in a tree, we do not have any cycle. So if we remove this particular edge, right, then it will look like 3 and then its node is 1 and 2. So this is a tree, right? If we remove this edge, then it will look like 2 is the root node and 1 and 3 are the child nodes. If we remove this edge, then 1 will be the root node, 3 and 2 will be its child, right? So then that means all of these three edges can be removed and our graph will become a tree then, right? But which one are we going to return? Which is occurring at the last in our edges vector, which is this particular edge, right? So this will be our answer in this particular case, right? Then if we check over here, so can we remove this particular edge? If we remove this particular edge, will it form a tree? No, because then this will be one component and this will be one component, and the tree is a connected component, right? So then that means this edge cannot be removed. But we can remove all of these edges because these are forming a cycle. If I remove this, then also it will be a tree. If I remove this, then also it will be a tree. This, if I remove any of these, the resultant structure will be a tree, right? So these four edges are these ones, right? So the last one is 1 comma 4. So this is our answer in this particular case, right? So this is what we need to identify. So now how are we going to solve this? So as we have already identified that adding an edge to our tree has resulted in a cycle. So we just need to identify where that cycle is being formed, right? And in that particular cycle, which is the last edge in the input that we need to return, right? So now few observations to note over here that when we have a tree, let's suppose something like this. So how many nodes are there? 1, 2, 3, 4, 5, 6. 6 nodes and how many edges? 1, 2, 3, 4, 5. 5 edges, right? So basically in a tree we have n nodes and n minus 1 edges. And since they have added a new edge into the tree which didn't exist before, so now how many edges will be there? N edges, right? So we can say that whatever is this count given to you, that is also the number of nodes in your graph. 3 edges are there, so 3 nodes we have. 5 edges are there, so total 5 nodes are there, right? So this is the observation that we have n nodes and n edges. Now to solve this, the brute force idea is that what you can do, you can take each of these edges, right? First, let me consider 1 comma 2, right? So what I can do is that I can apply DFS over this graph by not considering this as an edge, right? If we remove this particular edge from this graph, and we can check that is this a connected component and it is not having any cycles, right? So basically, if it is a connected component and if it is not having any cycle, then that means this edge can be removed, right? So this will be our answer. But since we want to identify the last edge, so we will keep on moving till the end, right? So then we will check for this one. So if we remove this edge and then we apply DFS over our graph, then we will see that it is a connected component and there are no cycles. So then that means this is our answer. Then we check for this one. Again, this can also be removed. So this can also be our answer. Then we will come here and we'll check this can also be removed. So this is our answer. Then we'll come here. For this, we will identify that this cannot be removed, right? So then we'll move further, but there are no edges to check. So this was our last answer. So this is what we will return, right? But here you will be applying DFS after considering each of these edges, right? So basically n times you will be applying DFS. So that will go somewhere around n square, right? So we will try to optimize it. Now there is a very good algorithm known as DSU, which is disjoint set union, known as DSU. Now this is a very good algorithm to apply over here because it can identify whether adding a particular edge is forming a cycle or not, right? So basically in DSU we have two things. One is a find function and one is a union function, right? So basically what happens is that in DSU, first of all, we consider all of the nodes as single components, right? So basically 1 alone is a single component, 2 alone, 3 alone, 4 alone, and 5 alone. This is how our nodes are, right? And then with the help of this union function, we try to join them as a connected component. Basically, we have separate components, right? And then we join them using this union function. And this find function is used to find out the parent of a particular node, right? So basically, what do we do in this algorithm is that, as I said, all of our nodes are separate components initially. So we have 5 nodes, 1, 2, 3, 4, 5. Let me give the names 1, 2, 3, 4, 5. So these are our 5 nodes, right? And then we maintain an array for storing the parents of these nodes. So we also maintain an array over here. So this is the parent array that we maintain, right? Here we are having 5 nodes. So these are the 5 nodes. This dummy node we have created because the indexing starts from 0. So these are the nodes, right? Now in this parent array, we store the parent of each of the nodes, right? So initially, as I said, all of the nodes are disconnected, right? So we can consider that the parent of each node is itself. Basically, we can say that 1 is the absolute parent of itself, right? And 2 is the absolute parent of itself, and so on, right? So initially we keep all the values like this: 0, 1, 2, 3, 4, 5, right? We are considering the node itself as its parent, right? And then what do we do? So as we have all of our edges over here, we try to join these nodes on the basis of these edges using the union function, right? So see, the first edge that we have is 1 and 2, right? So what do we do is that from this parent function or this parent array, we find out that what is the parent of 1 and what is the parent of 2. So right now parent of 1 is 1 and that of 2 is 2. Since their parents are different, 1 and 2 is different, then that means right now 1 and 2 are part of different components. So then that means if we join them together, right, then it won't create a cycle because right now they are part of different components, right? So what do we do is that we join the node 1 with node 2. Basically, we join these now, right? And now since we have updated this, what do we do is now if you see the parent of node 2 has become node 1. So here in the array, we update its parent to 1. This is what we do. Then the next node that comes is 2, 3. Then that means we need to join this node and this node. Right now, these two are part of different components. And how will you identify that? Through the find function. Find function will return you the parent of 2 and the parent of 3. What is the parent of 2? So it is 1. So we will go to 1. And what is the parent of 1? 1 itself. So ultimately, the parent of node 2 is 1 and that of node 3 is 3. So the parents are different, then that means these are part of separate components and they can be joined together, right? So we join them. But now, when we will join it like this, what will happen? That our height will increase, right? Now we will add node 4, then some other node. So this height will keep on increasing. And then when you will have to identify the parent, then you will have to go all the way to back to identify, right? So that will increase your time. So to make this more efficient, we apply the concept of path compression, right? We apply path compression along with union by rank, right? So basically in that, what do we do is that we take another vector known as a rank, right, or an array, which is of the same size, and initially we keep all the values as 0. So this basically denotes that what is the rank of each of the node, right? So when we had inserted the first edge, which was 1 comma 2, at that point, what we will check is that what is the rank of 1 and what is the rank of 2, right? So right now both the ranks are same. So in that particular case, we can either make 1 as the parent of 2 or 2 as the parent of 1, right? So for now, we will create 1 as the parent of 2. So when we are doing this, what we will do is that we will increase the rank of 1 by 1, right? Basically, whichever is the parent node, its rank we will increase by 1, right? Now when you will have to do the union of node 2 and node 3, basically you need to insert this particular edge. So you will check that what is the rank of the parent of 2 and what is the rank of the parent of 3, right? The parent of 2 was 1 and parent of 3 was 3. What is the rank of 1? 1. And what is the rank of 3? 0. So whichever is having more rank, basically this one, we will make this as the parent, right? So basically we will make 3 as a child of 1, right? So now the parent of 3 will become 1. So this is because we are flattening our structure over here. Otherwise, if we would keep on putting like this, it would create a linked list kind of a thing, right? And that would not be efficient. Doing this, it will make this entire process near to constant time, right? So once we have done this, what do? We will take the next edge, which is 3 comma 4, right? Then we check what is the parent of 3? 1. What is the parent of 1? 1 itself. So the parent of 3 is 1 and the parent of 4 is 4. Then we check the ranks. So the rank of 1 is 1 and that of 4 is 0, right? So we make 1 as the parent of 4. So we connect 4 over here and the parent of 4 becomes 1. Then the next edge is 1 comma 4. So here, what is the parent of 1? It is 1 itself. And what is the parent of 4? 1, right? So now that we know that the parents are same, so then that means these nodes are already part of the same component. And if we try to add one more edge over here, then it will create a cycle. So whenever we get same parents, then that means this is the culprit edge, right? If we add this particular edge, then a cycle is being formed. So whenever you get that, okay, if I am adding this particular edge, their parents are coming out as same, then that means this is our answer. Why is this our answer? Because we are moving from left to right, and it is guaranteed that in our graph there will always be only one cycle because they have inserted only one extra edge, right? So whenever you are encountering an edge for the first time due to which here a cycle is being formed, then that means this is the last edge in your input, which is the culprit, and you can return it in your answer, right? So this is what the union find algorithm is. We will look at the code to understand better how are we going to approach it. So here basically we use the concept of rank to make our code more efficient, and also we do path compression. So basically what do? If in the parent array, let's suppose instead of creating 3 as a child of 1, we created it as a child of 2. In that particular case, the parent of 3 would be 2. And when you would have to find the ultimate parent of 3, what would you do? First, you would go to 3. Then you see, okay, it is 2. So you would go to 2. So you see, okay, it is 1. So you go to 1. And then you find out that, okay, the parent is 1. So this would increase your time, right? So in the find function, what do is that when we were trying to identify the parent of 3, so we update it here as well, so that the next time when we want to identify the parent of 3, we get it from here itself. We do not have to go all the way till 1, right? So that is how we are going to solve this. Let us now quickly look at the code. So first of all, let's take the number of nodes, which will be equals to edges dot size. And then for our DSU, we need two vectors, right? One is the parent vector, right? and other one is the rank vector, right? Now they are going to be of size n, right? We can run a for loop of I over here starting from 0 going till less than equals to n, right? Because the labeling of the nodes start from 1 till n, right? So now what we can do is that in the rank we will push back 0 because initially we are keeping the rank of all the nodes as 0, and in the parent we will push back I because we are considering that the absolute parent of a node is that particular node itself initially, right? And then what we will simply do is that we will iterate inside our edges. So for auto edge in edges, so we will pass the edge to our union function, right? So if their parents are same, then it will return us false. Then that means this is the culprit edge, right? So what we will do is that we will check that if not of union set, because union I think might be a keyword, so that is why we can keep the name of the function as union set, and we will pass edge of 0 and edge of 1, the two nodes, right? So if this is returning us false, then that means this edge is our answer. So not of false will become true and we will return this edge, right? Now it is guaranteed that there will always be one such edge, so our answer will always return from here itself. But for avoiding compilation errors, we will also have to return something from here. So this dummy empty vector we can return, right? Now we want to create this function union set, right? This is going to return us a boolean, right? And it is receiving two nodes x and y, right? Now inside this, we need to find out the parent of x and the parent of y, right? So for that, let's create a find function which will receive a node and it will return us the parent of this node, right? So here what do we do is we check that if the parent of this node is not this particular node, but basically some other node, then we go to that node. So we apply recursion over here over the parent, right? And whatever it returns, we update it here. Okay, so this is basically the path compression concept, right? And then here we return parent of x, right? So basically our base condition is that when the node itself is its parent, when these two values become equal, that is our base case, right? So this is how we identify the parent of a particular node. And then here what do we do is that the parent of x will be equals to find x and the parent of y will be equals to find y, right? Now here we need to check that if the two parents are equal, then that means they are forming a cycle, they are part of the same component. So we will return a false from here, right? Otherwise, we will combine those two components, right? How are we going to combine? On the basis of the rank. So first we will check that what is the rank of parent of x. If it is less than the rank of parent of y, then in that particular case, we will do this. Basically, we will make the parent of y as the parent of x, right? Otherwise, we will check that if the rank of parent of y is less than the rank of parent of x, then in that particular case, we will do the opposite of this, right? Else, if the rank of both the parents are same, then in that particular case, we can make any one of the nodes as the parent. So let me write y parent over here and x parent over here, right? And then we will have to increase the rank of x parent by 1. Basically, whatever is here, its rank will be increased by 1, right? And at the end over here, we can return a true, right? So this is how we can solve this problem. Let's try to run this now. So the test cases are accepted. Let's try to submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.